So NASA defined, so it combined, or let's say coupled these two concepts together, and then they came up with a very comprehensive definition of digital twins. And I would like to go through this. So this was called as an first of all, it was integrated, it was multi-physics, it was multi-scale, a probabilistic simulation, right? So these are very heavy words. I won't delve deeper into that, but just try to see multi-physics, multi-scale, right? So there are different 5 scale. There are, let's say, there is an atomistic scale, right? There is nanoscale, and then there is macro, micro, all of these different kind of scales, right? Probabilistic, I will talk a little bit about it a bit later. But this was kind of a definition that NASA gave back in 2012. But after that, this concept came in literature, a lot of people started working on it. And now, as I mentioned, right, we have, so this is let's say an old number, but about 40 to 50 different definitions of the digital twin, right? Based upon what kind of an industrial use case. If you are using a digital twin in a process industry, they are defining it in a different way. If you are using it in automotive industry, they are defining digital twin in a very different way, right? So that is why there are different definitions. But the core concept is still the same. So what is this core concept, right? So from a purely structural point of view, and keeping in mind that we will be talking about wind turbines, so this is how you can define a digital twin. So this is the definition that I primarily use for my research, right? So this is the physical system. So what is the physical system? This is a very simple geometry of a wind turbine. This is my tower, and this is the lumped mass, right? This is the lumped mass, which is your, again, as I showed you, the entire nacelle and rotor, right? So you have a physical system over here, right? So this is on this you put sensors. What then you do is, then you create a virtual replica of that system. What is that virtual replica? Again, your 3D model. And then there is a concept of virtual sensors, right? So I can explain it a little bit. And then what is happening? So from the sensors to the actuators, this is called as your data is being transmitted. On the wind turbine, we have something called as a SCADA. SCADA stands for Supervisory Control and Data Acquisition System. That is very widely used, right? So that will generate, let's say, a data point every 10 minutes. And in data point, what you'll have, let's say, what is your RPM, what is your wind speed, right? How much electricity are you generating? All of these. So there are about 100 different parameters that a SCADA system is generating. And generally, the industry practice in wind turbine condition monitoring is that every 10 minutes you generate this data, right? So now this is called as a digital thread, right? So what will happen, I will show it to you a little bit later, that whenever there is some kind of, let's say a deflection is happening because of an external load, because you have sensor data here, this kind of deflection will also be replicated in your virtual model, right? So when my physical system is deflecting, my virtual system will also reflect in real time. Okay. So now if I have to define a digital twin, I will say that the 3 important points there is that there is a physical asset, there is a virtual replica, and then there is a digital thread which is connecting them, right, in a real time. And you can use this not just for simulation, but for optimization, prediction, monitoring, controlling, and at the end to improve the decision making, right? So I will show you this as well a little bit later, right? So this is a very simple definition of digital twin. So now going back to our timeline. So here you can see that 1970s simulations were being done. They were not connected to the physical system, right? Only you were doing simulations and generating data. Then what happened? You connected and back in 1970s, simulations were primarily used at a design phase. But then in 2000, starting from 2000, even not just for design, but you integrated manufacturing, and that is what came into the picture. And digital twin is a concept, let's say a bigger bubble within which all of these are encapsulated. This CAD, CAM, simulation, everything is encapsulated in that, right? And you can use digital twin for what? the first important thing is that it will always be real time, right? And there will be a data flow continuously in both the directions, from physical to virtual, from virtual to this. And you can use it toward through the entire product life cycle management, right? So this is a digital twin. Now, again, to confuse you a little bit more, so when this definition of digital twin came to the picture, more researchers, or the more, let's say, people from academia, they said that, okay, we understand that there has to be a real-time interaction, but we see that it is not possible that your data flow between a physical replica, between a physical system and a virtual system, it is not happening automatically all of the time, right? So then, based upon how your data is being transferred from physical system to virtual system and vice versa, whether it is manual or it is automatic, there came these four different concepts came to the picture, right? So digital model is, as I've explained, and we all know it very well, you have a physical system, you create a 3D model of it, and then what will happen, you'll have a sensor data, right? You'll have, let's say, set of parameters, you'll say wind speed is this much, right? And the wind direction is this much, and then you run through simulations. So I will create a 3D model manually, and then I will with this Excel sheet, I will put it manually, and then it will give me data, and then I'll take that data, and then I'll change my physical system, right? So all of this is, there is a lot of human intervention is involved. So if this is happening, then this is called as the digital model. Digital generator, on the other hand, is, let's say, the modern simulations that we are using. So I will feed my data into my, let's say, simulation software manually. But then what will happen is, from the virtual system to the physical system, this data will be transmitted automatically. So then this is called as a digital generator, because I'm generating data, right? Digital shadow is opposite. When your data from physical to virtual is automatic, but in the opposite direction, it's manual, this is called as a digital shadow, right? On the other hand, here, this is a digital twin, which means here, what is happening is you have automatic data flow in both the directions. So I will show you an example of digital shadow, and then I also show you an example of a digital twin, right? You might think that how is it possible that from a physical system to a virtual system, this is happening automatically, right? So I'm just going to show you an example of that. And this is one of my colleagues in another university in Norway. So we taught this course together, and this is the kind of so I have a small, I don't know how clear you can see, but let me explain you. So what we are trying to do is, so again, we have this same lumped mass. So this is the, let's say we are saying that this is the tower of a wind turbine, and here you have a lumped mass, which is representing the top mass of the nacelle and wind turbine blades, right? So then what we try to do is, we created this 3D model, a very simple model, right? So it is a cantilever beam where you have the point load at the end, right? But it is in a vertical direction. So we connected a few accelerometers to this, right? And then this sensor data will be fed directly into the virtual system, right? So now notice what we are trying to do is, we are not saying that, okay, I will collect the deflection, and then I'm putting that deflection manually. I'm not typing anything in, right? So I am showing you an example of a digital shadow. So that is what I'm trying to say. From a physical system to a virtual system, there is an automatic data flow, right? So how it will happen. So now you can see, when I will run this video, so you will see whenever we are deflecting this to this direction or this direction, there will also be a corresponding and equal movement in the virtual. So this is a physical space, this is a virtual space. So now you can see, right? So this is an automatic data flow from physical to the virtual, right? So there is no manual intervention. But then I am not, so this is not a digital twin, right? Why? Because a digital twin would be that there would also be an automatic data flow or some action from virtual to physical. That also I'll show you a little bit later, right? So this is an example of a digital shadow. So now an example of a digital twin, right? A general, very pictorial representation. And here, why I want to show you this picture to you guys is because I talked about other hype terms, right? And questions that I asked, that what is the role of big data, right? In the in this the entire framework for digital twin. So here you can see that you have a physical world, right? There is an environment. Physical world is my wind turbine, right? So how then there are a lot of sensors, there are a lot of actuators. So edge processing, why do we need edge processing? So those of you who are working with in IT or CSE, you clearly know that although the primary purpose of edge processing is when you want the things to be happening in real time. So that is why, right? So this communication, so you are generating sensor data, you are communication can happen through different means: Bluetooth, Wi-Fi, satellite, right, or a cable. And then you have a virtual replica of the physical, right? And then this virtual model, here what we try to do is we are using AI or deep learning. We call them surrogate models, right? Because all of us can agree that the CFD or FEM, they are very accurate, and their accuracy depends upon the mesh size, how many number of nodes you are using, right? So they can be highly accurate, right? But the point is that this accuracy comes at an expense of time. If you have a 3D model where you have used say 1 million right, 1 million meshes or nodes, and then when you try to run it and compare it to a model where you have just say 10,000 nodes, right? So clearly the one with a refined mesh, it will be more accurate, but it will be very time consuming. So during my PhD, my main aim was that how you can keep the accuracy of these highly fidel FEM models, because I was working with FEM, but how you can improve the predict how you can improve, let's say, or reduce the time of prediction. So that is where AI comes into the picture, right? So surrogate models are used over there. And then again, let's say I told you that just SCADA data that is coming from these wind turbines and going over here, every 10 minutes you are generating one data point which is having, let's say, hundreds of features. So if the lifespan of a wind turbine is 20 to 25 years, so you can see that the data size is humongous, right? It is of the orders of terabytes. And it is not just SCADA data, there is also a lot of other kind of sensors, right? There is a sensor there are vibration sensors on your gearboxes, there is thermal sensors, right? So all of that data is also coming into the picture, and that is why you need to adopt these big data technologies, right? The 5 V's, as we know about the big data. And that is, you can see in this simple representation, that this is how your big data, AI, they are integrated in this concept of digital twin, right? So if you want the digital twin to be successful, you need edge processing. You cannot rely on cloud computing. You need cybersecurities. About an year ago, there was a huge news in Europe that one of the wind farms, its cybersecurity was compromised, right? So we need people from different domains. We need people from mechanical, we need people from electrical, we need people from definitely CSC and IT. If we want these digital twins, we need people from automation and control, right? When we are talking about the digital twins. And then here you can see you have the users, right? So this is a very simple pictorial representation of this. So again, most of the researchers who are working with digital twin, they came up with, as I mentioned, different kind of terminologies. We have discussed about digital shadow, digital twin, but they also, so people who are working on this product life cycle, right? Let's say your automation or automotive industry. So how they said that they defined digital twin based upon the system, right? There can be a simple component, there can be a digital twin of a component. Then from a component you make a device, and from a device you make a system, right? So here you can see. So the example here is of a let's say the battery packs. So at a component level, you can have the digital twins for raw materials, where or for the manufacturing processes, right? Then you assemble these different cells. So here is the cells into the battery packs, right? The battery modules. Let's say in the Tesla Y model, there are about 6,000 batteries like this over there, right? And then these devices, for example, in a big wind turbine, as I showed you, there are multiple components or there are multiple devices, right? So they perform one system. Another level is system of systems, right? That is also what people are talking about. Wind farm is a system of system. Wind farm means when there are hundreds of wind turbines at one particular location. That is called as a wind farm. And I was talking about the scales, like one of the in the definition, one of the word was at multiple scales. So we can start from micro. Now people are also going back to, let's say, atomistic level, because we have those of you who are dealing with the simulations. You see that there is molecular dynamics is there, then there is atomistic models, right? And then at the continuum level, there are these FEMs and CFDs that we are doing, right? So these are the different kind of scales we are talking about, starting from a micro to the meter length scale, right? Example is again of an electric car. So in Norway, about most of the new cars that are being since 2023, that are being sold, they are fully electric, right? Which means that the purchase of, or the customers are not buying petrol or diesel cars, rather everyone is going for these electrical cars. So that is a very big these cars are a very big part of the Norwegian society. So over here you will see that, and I myself, I have an electric car, so I'll show you a video which I can say is a fully functional digital twin model, right? So what we are doing, again, comparing the top image to this image. So all of these electric cars, what they have is, they have at a, let's say, at a device level, right? At a device level, for the battery packs, there is a different simulation model, right? For the aerodynamic performance, there is a different model, right? How much energy are you consuming? So, and how you should optimize it, there is a different model for that. So there are a lot of, in the virtual space, there are different models, and they are actually giving you a lot of information. So an example for Tesla, let's say if some maintenance activity has to be done, whether it is even just the pressure, how much is the tread depth of my pressure, right, of my tires. So even there is a sensor for that. It will come, right? Let's say my wipers are not working. So in these electric cars, you don't take them to the workshop. Everything is fixed with the help of a software, right? Just like for your Apple iPhones, there is a software upgrade. So all of this is happening, and let's say in the head office in the US, and the car is being driven in Europe, right? So you can see that there is this, from the virtual, your physical. So now what I'm talking about is how from the virtual you are trying to control the physical system, right? So with this app, right now I am in India, but with this app I can open the, let's say, the bonnet of my car with the help of this, right? I'm giving a command from a virtual system to the physical system, right? So that is how an automatic data flow is happening from the virtual space to the physical space. And when this loop is completed, then it becomes a fully functional digital twin, right? So that was one classification, depending upon whether you are at a component level, you are at a system level, or you are at a device level. But then another researcher, so these researchers, again, they are from the University in Norway. So they came up with this definition or this classification of digital twin. I won't delve deeper into this, but again, their primary aim is, or their use case is, oil and gas and wind, right? So they came up with this, right? And they are using digital twins for predictive maintenance. That is the only purpose, right? So here you can see you have a standalone. Standalone is basically just a 3D model of a wind turbine, which is in your virtual system. That is standalone. Descriptive is, which is describing something, right? When you are using some kind of a sensor data on the CAD models, right? Diagnostic is, as you can see, when you have coupled it up with a condition monitoring, and when you can make decisions for that. Predictive is what will happen in the future. Prescriptive is what kind of action should I do in order to whatever you have predicted. Let's say I go to the doctor, he diagnoses me, let's say that, okay, you have you have this, okay, you have tuberculosis, for example, right? So then he can also say, so that is the diagnosis. Predictive would be that, okay, your lifespan is only 5 years, right? If you continue with your lifestyle the way you have, your lifespan is 5 years. Prescriptive would be that, on the other hand, if you change your lifestyle, if you jog, you walk, you take this medicine, then your lifestyle can be improved. And that is a prescriptive. Autonomous is like, without the human intervention, everything is happening. As we know that there are self-healing materials, that is the kind of the thing. Autonomous means that particular action, the prescriptive action, is also taken by the system, and then it improves its health. So that is based upon that they have categorized the digital twin. That was the classification. Now if we try to map this classification with what we learned little bit in the earlier slides, that how is it connected to the digital model, digital shadow, and a digital twin. So you can see the fully autonomous can only be classified, a fully autonomous system can only be classified as digital twin. And fully autonomous means the data flow between physical and virtual is automatic, and from the virtual to the physical is also automatic. There is no human intervention, right? On the other hand, from descriptive to prescriptive, that are more into the digital shadow. So I showed you an example of digital shadow, right? From physical to digital, there is direct. On the other hand, this way is not direct, right? And the standalone, as I mentioned, this is just a simple digital model. Everything has to be done in a very physical way, or with the help of the humans, right? So this is how we are mapping these two. Now, in terms of maturity, so we discussed that in 1960s the concept of physical twin came into the picture. In 2002 there was mirror spaced model. In 2012 the concept or the term was coined digital twin, and since then its adoption and its research has exploded in a very exponential way, right? So here you can see how the digital twin has matured and what kind of value it has generated. So an ideal case would be, here you can see a fully autonomous system which is capable of, and now with the help of this agentic AI, you can see that it is possible that you would have a fully autonomous system, right? So but this slide over here, this is more of how different technologies will be enablers for the wide and adoption of this digital twin, how they can be used. So you can see that AR and VR. So I am currently working a lot with virtual reality, and the point there is that we have this virtual space where you can go into and see how the wind turbine looks like, right? That is what we're working with. In terms of an industry adoption, you can see that different industries are adopting, starting from simple agriculture, aerospace, as I mentioned, they were the first adopters, right? In construction, people are using it. Cities, Singapore has for the entire, because it's a very small country, so it is possible to make. So they have a digital twin of the entire Singapore city, or if you say, let's say, even at a country level, right? And then they can see, so what all can happen in the digital twin model, or a digital twin of a city. It's let's say it's raining, right? And you know that, okay, there are 4 water treatment plants. So which one should be used? So you can easily forecast, because you can see the forecast for the next 3 days. You will say that on this day we will use this tunnel, right? Or this water treatment plant. On the next day we will use this particular. So these are the kind of decisions that these stakeholders are taking advantage of these digital twin, right? So that is at more at, let's say, industry level. It's construction industry is using it, so they are extending this BIMs. BIM is basically a technology, as you might be aware. It's basically just providing an information, right? Okay, what kind of material has been used, right? Where it has been procured from, all of this, right? But when you can feed in sensor data into this, and let's say if the wind is blowing with this particular speed, what will be the deflection, right? And let's say if a earthquake of 5.5 Richter scale is happening, what can happen? So all of these what if scenarios can easily be done with the help of this. So again, this central figure over here, you can see again these 3 things: a physical, a virtual, and data, right? So there is a continuous interaction over there. And electricity, I've already showed you some of the examples from this wind turbine, right? So now this is something I want to tell you about, is that Tesla, they have digital twin for all of their cars, right? So what I'll show you, this I recorded when I was driving to my office. So this is the tunnel. So here you can see when you are driving, you have this big LCD in front of you, right? Which is like a big iPad, like let's say 14 to 15 inch. So let's say this is the car that I am driving. So as I am driving in real time, it is also showing me that, okay, there are trucks in here, right? So if I just click on this, so these are the trucks over here, and here you can see this is my car, right? So I can drive this in a fully autonomous way, right? Without using steerings, without using any accelerator or brake. It can, so all of this speed that you are seeing, so this can drive itself. It can take curves itself, right? So this is a fully autonomous agent in itself, right? And as I mentioned, that with the help from this, which is my car in the virtual space, so I can open the bonnet of the car just clicking on the digital model and it will open. I can close it, right? And the, let's say, the lag that I'm talking about, right? Because it has to be real time. So if I have parked my car, right, in the park mode, so then I will see that when I am, opening the window of my car, even in the digital model, it will open. When I'm closing the window of my car, it will open. When I'm opening my door, it will open. When I'm closing, and I can do not, so it's like, it's not that only in the physical system when I'm making a change, my virtual system is changing, but opposite is also true. I can open my door just by clicking on the digital model as well, right? So there is this continuous flow of the data that is happening. And as I mentioned, that if a software upgrade has to happen, so people who are sitting in US, they can easily upgrade. They can control my car in reality. That is the fact, right? Because they can see, if they want, they can see and all of the things in the digital model that is with them, right? So what I'm seeing here, they're also seeing the same thing, right? So to me, this is something the closest, and how my life is impacted with digital twin. And this is a highly safe. So I'm not here to promote any car, but the point is that digital twin are being used. They're not a hype anymore, right? So if I go, yeah, so this was it. Now for a power system, which again is, in my case, it's a wind turbine. So this is the kind of a framework that you can use, right? So you will have model-based tools, right? Model-based, as I mentioned, these Simulink models. You will have empirical tools. Empirical could be your experience, right? Your subjective opinions, right? And then you will have data-driven tools. All of these machine learning, big data, your sensor data, they come into the picture, right? So digital twin uses all of these technologies. As I mentioned, that there is, all of these are enablers for digital twin, right? And then you would have actuators, you would have sensors, there is a physical object, there is a digital twin. So this is a data flow. So your sensor data goes through these communication channels into the digital twin model. Then you run these simulations in these. So here all of the data is stored. You do all of these what if scenarios. So what if scenario in the case of wind turbine would be that if the wind is blowing at 30 meters per second, right? So you can easily simulate it, that how much will be the load on the main shaft or the main bearing, right? And then based upon that, you can take these decisions. You can, with the help of actuators. So I can say that at 25 meters per second, when the wind speed is there, right, you should apply the brakes, because in the wind turbine there is also brake, right? So this decision can happen. You can easily put that logic inside, that whenever the wind speed is 25 meters per second, the brake should be applied, right? So with the help of actuators, that will happen. And now what will happen is that brakes will be applied, and your physical object, which in this case is wind turbine, it will slow down, right? So this completes the loop, and all of this is happening in a very autonomous way. But we as humans, we can easily monitor them with the help of all of these interfaces, right? A big control systems are there, big control rooms are there where you can see. So although these are autonomous systems, but there is always this, one button which humans can, if your system is not behaving the way it is supposed to behave, we can always intervene in between, right? So that is one thing. Now, this is primarily, I think, the second last slide. So this is a 3-minute video just to show you that how virtual reality and how your digital twin models are being used, right? So this is something which we are working on. I think this is something which we are currently working on, right? So this was a very brief. Again, sorry. Yeah. So this was a very brief, and this is my last slide. So if so, we started with this that okay, in back in 2018, digital twins, if you remember, they were here, right? People expected a lot of it, a lot out of it. So in the next 7 years, right? Let's say from 18 to 2025, if you have to ask me, and as I've seen the industrial use cases and even in the research, so I think that they have easily moved to this. So now people are, because in 2020s during this corona time, people were like, okay, just hype, they are of no use. But ever since then, a lot of adoption has happened, especially in the process industry, right? And also in now in the renewable sector, people are using these digital twins, and there is a huge scope. There are multiple reports which are talking about that, 150 to 60 times there is a huge scope of the adoption of digital twins. So that is why, at least for myself, I've decided that, let's say, next 30 years of my career, I will focus only on this. So it's a very I like to work in this field, and the primary reason is because there is integration of multiple technologies, as I've shown you. There is AI, there is virtual reality, so you can tap into different kind of sectors and different kind of technologies. And so it's a very, let's say, a very important. If I have to say that, okay, it's a very important concept that people in industry, they want to use it, but they are a little bit scared. So we as an academicians and researchers, it's our duty, at least, to use it at a lab scale, and then prove its functionality at an industrial scale. So we have found some success, but again, I'm pretty open to all of the collaborations, and if you find any use cases, I would be very happy to collaborate with all of you guys. So these are some of the references. So this is a handbook of digital twins, which was written by one of the researchers from Sweden. And when I was working in DNV, we work on probabilistic digital twin. You can have a look into this as well. And these are some of my colleagues who are working with the digital twins. Yeah. So yeah, that is all from my side. So if you guys are still confused, so in July I'll be back to Norway. So I'm pretty open if you want to work in this direction. So I'm happy to collaborate with you guys. So that is it from my side for today.
Thank you, Professor, for such a wonderful and informative, highly knowledgeable. Even it is a new concept for many of us. So thank you very much for your wonderful lecture. So I would like to request participants if you have any question, if you want to interact with the professor. Then I think Pahul Parit, uh, you have me.
Can I ask a question?
Sure, sir, sure. Please go ahead.
Um, Thank you, Dr. Arvind. It was a wonderful lecture. And, we are still new to this concept of digital twins. My only question here is that, so you talked about digital generator, digital shadow, and digital twin, you know, and are we using any the concept of digital generator also? Digital generator.
Yes, sir.
Yeah.
So all of these, let's say, so we are using simulations, right? We are using simulations. So that is we are using these simulations, let's say CFD, FEM. So that is a digital generator. So we are using that in order to generate data automatically. So that is a digital generator. So that we have been using quite a lot, right?
Okay. Yeah. Are we making the digital twins of our, for example, you talked about the aeronautical systems, aerodynamics, where these systems actually they started. I mean, what was the motivation for these? What they started from the aeronautic system. So recently we had, I mean, just for the sake of curiosity, I'm asking. So recently in India we had a very aircraft crash at Ahmedabad airport.
Yeah.
So can we think of having digital twins for our these airplanes? I mean, these are also dynamic systems. So can we think of course, in the news we are hearing there is a certain loss of power, there is a certain loss of thrust. So could, if the digital twin would have been, we could have formed a digital twin for this aircrafts or the aircraft, could we have saved that aircraft from the damage?
Yeah, see, sir, that is, I think that would be an ideal case and it is pretty possible. But then again, the answer to this could be at multiple levels, right? It is also the trust in a system itself, in this technology itself. For example, Tesla trusts it because, but probably Boeing, they don't have, because again, Tesla is known for like hardcore engineering. They are pioneers in what they're doing. But as, again, based upon what I have seen on YouTube, or let's say even you'll find multiple articles which are talking about the engineering practices that are happening at Boeing. So they are not primarily doing it in a very effective way. So if you want to somehow, overshadow of something unethical that you are doing, then you would not use concept like digital twin, because that is, you are mirroring everything what you are trying to do. So it's also about the adoption. But I fully agree with you that if you would have a digital twin model, there would have been a possibility that they could have predicted this kind of abnormal behavior of the aircraft a little bit earlier. But there is also one problem with this digital twin, and that is, let's say if your sensor data failed, right? Because in this case, the system itself is failing, and if that, let's say, the communication layer breaks, then this kind of technology is handicapped, because you're relying on communication network as well. So especially in offshore wind farms, which are in the oceans, this is one of the biggest challenge which we are facing, because there you don't find like 5G networks, etc. Right? So that is a big problem. So in order to circumvent that, then there are different kind of technologies that we are trying to investigate. But I fully agree with you in that sense that it is possible. But
I think the implementation of digital twin is very capital intensive also.
Yeah, that is my next point, because there is huge cost involved in that, right? At the end, when we say big data, cloud computing, you are relying primarily on these big big three, right? Google Cloud, and you know that one of my students were doing his master thesis, so there they were charging him like $200 per per GB of the RAM used. So it becomes pretty intensive in terms of costs. So you have to justify that, especially for companies. Besides being safety critical, they also have to be economically viable option for you. So then they will say that okay, जब तक चल रहा है it's okay.
Right.
It is a mandatory requirement. Then we'll see.
And just one more question. You just
Yes,
touched upon the concept of edge computing,
Yes,
and we know what is cloud computing. And what heard is the edge computing is different from cloud computing. Can you just tell
Yes.
us, because I am
Yeah. Sir, edge computing. See, the point is, the whole you compute something and then you want to make a decision, right? So when it is happening far from, let's say, I am here in Kullu, and the decision maker is in Delhi, right?
Okay.
So then again a communication problem. There could be lag of 5 seconds. But if I'm in Kullu and if the decision maker is sitting in, let's say, just 5 kilometers away from me, then decision will happen fast because communication is smaller, right? But then the point is, in Delhi you have a let's say prime minister is sitting in Delhi, but SDM is sitting in this, right? So the power of PM is much more than the STM, right? So in this case, the bandwidth of edge computing is small, but of cloud computing is more. But the point is, the time taken by edge computing is much smaller. So that is why we are using edge computing.
Okay, because we have to take that decision in a very
In a very, very
time is
real
very
time.
important.
That is very important. Otherwise, there is no point of digital twin. अगर 10 सेकंड बाद आपको पता लग रहा है कि something bad is happening.
Right.
It
The
can
damage has
happen.
been ordered. Thank you.
Yeah.
Thank you, Dr. Arvind. Thank you. For that.
Yeah, okay.
Yeah, thank you, Professor. Let me also introduce you with the Dr. Rajiv Kukreja. He's also the chairman for this short-term course, and he's an associate professor in the Department of Mechanical Engineering. And his expertise in the VCR systems, and he's also expert in design and optimization of thermal systems. Yeah, thank you very
Thank
much,
you.
Professor, for your valuable time, and wishing you pleasant stay in your own valley, Himachal.
So, thank you, sir. Thank you. It was a pleasure.
Okay, thank you so much, sir.
Yeah.
Thank you.
Okay, sir. Take care, sir. Bye bye.
Bye, sir. So, dear participants, we'll resume the second day and second session from 3 p.m. So, I hope that you all will join on time. Thank you for your joining.